Before we go to the next section of this chapter, let me just introduce you to this term, valence electrons. We're going to go into a lot more detail, but let's just introduce it to you while we're on the subject of electrons. And by the way, what electrons do determines the chemistry. So chemists care a lot about electrons. Protons are important because they define the nature of the atom or the element, and they also have a positive charge, which is extremely important in keeping the electrons on the atom. But it is the movement of the electrons and where they go that causes chemical reactions. It is always the valence electrons that are involved in chemistry. These are what we consider the highest energy electrons in an atom, or in other words, these are the electrons that are furthest from the nucleus, so they are most easily plucked off or moved around because their attraction to the positively charged nucleus is the weakest because they're the farthest from it. Now, just as a recap, metals form cations by losing their valence electrons. And many of them, not all, but many of them do that so they can get the same number of electrons as the nearest noble gas. Nonmetals form anions by gaining electrons to have the same number of electrons as the next noble gas. And that's how we know the charge of our anions, by seeing how many columns away it is from our noble gas. 1, 2, 3. Now we're going to talk about the nucleus. I told you that electrons were the most important in chemistry, but the nucleus does have some weight, so to speak. Ha ha ha. No pun intended. There was a discovery that the same element could have atoms with different masses, and he called these isotopes. Soddy was the experimenter who discovered this. And for example, there are two isotopes, or two atoms with different masses of chlorine that are naturally occurring in nature. One has a mass of about 35 AMU. The other has a mass of 37 AMU. And the observed mass of all chlorine is what's known as a weighted average. And I'll go into a lot of detail in a few slides what a weighted average is. That's actually how I figure out your grade in this class, through a weighted average. But the atomic mass of the chlorine atom is considered to be a weighted average of these two different masses. So let's talk about isotopes. What makes the masses different? Let's go up here. What's different between a mass of 35 and 37? Well, the number of protons have to be the same if it's chlorine, and the number of electrons have to be the same because they're going to be equal to the protons. So it must be the neutrons. So this isotope has 2 more neutrons than this, since neutrons weigh about 1 AMU. Isotopes of an element are chemically identical. Heavier isotopes will move more slowly, but they will undergo the exact same chemical reactions. If we're looking at an isotope of the same element, they of course are going to have the same number of protons. That never changes for a given element. However, isotopes of a given element will have different number of neutrons, and because they have different number of neutrons, they will have different masses. Now, chemists and physicists talk about isotopes not only in terms of their element, but what's known as their mass number. And a mass number is simply the sum of the protons and the neutrons in the nucleus of an isotope. So before we look at the math, let's look at some symbols here. We know the atomic number is the number of protons, and that's symbolized by capital letter Z. Now we're learning about the mass number. The mass number is so called because the protons and the neutrons make up most of the mass of the atom. But it is a number. It is a whole number the number of protons and neutrons in the nucleus, and it is symbolized by capital letter A. Now, in nature, there are certain percentages of isotopes that are found that is unchanging, and here's an example of neon. Neon we know is a noble gas, and it has 3 isotopes. These isotopes are indicated not only by the symbol of the element, but also by its mass number. So neon has 3 naturally occurring isotopes: neon 21, neon 22, and neon 20. 21 and 22 and 20 are the mass numbers of the isotopes, and they're found in certain percentages. Neon 20 is by far the most abundant, and it has a naturally occurring percentage of 90.48. Neon 22, smaller at 9.25, and neon 21, the smallest, at 0.27. All of these abundances are going to add up, all of these percentages are going to add up to be 100%. And whenever you have a sample of neon, whether it is in a sign or in a gas cylinder in a laboratory, that sample of neon will always have these 3 isotopes in these 3 percentages. So let's look at these 3 isotopes broken down. This is the symbol that we saw in the previous slide. It can also be written in this format. Remember that when we were writing charges, they were on the right upper hand side of the symbol. When we're talking about the nucleus, we always look at the left hand side of the symbol. Physicists often use this symbol because they don't know how many protons are in an atom. They always have to write it down. But chemists often use this because we are much more familiar with the periodic table. So the symbol, this format of the symbol would have the symbol of the element. Below is the atomic number, and above is the mass number. So down here would be Z, and up here would be A. So here's neon 21, here is our atomic number and our mass number. Atomic number, mass number. Notice that the atomic number is the same for each, because anytime you have the symbol, you always have 10 protons. And which of these do you think is going to be the heaviest? Of course, neon 22. It has the highest mass number and the most neutrons. So if we're given either this symbol or this symbol and a periodic table, we can figure out the protons and neutrons. The protons is easy. All we need is a periodic table, neon, 10 protons. To figure out the number of neutrons, we subtract the protons from the mass number. Because remember, the mass number is the number of protons and number of neutrons. So if our mass number is 20, and 10 of that is from 10 protons, the other 10 is from neutrons. If my mass number is 21, 10 of that comes from my protons, the other 11 from neutrons. If my mass number is 22, 10 of that is from my protons, the other 12 comes from neutrons. So subtract the number of protons from the mass number to get the number of neutrons. And then when we add these two together, we should get the mass number back. And then here's the percent which of the isotopes which is known as a natural abundance. This has to be given to you unless you're dealing with isotopes where there's only 2. If one percentage is given, you can calculate the other by simply subtracting it from 100.